In chapter 2 is about the resistive circuits, which means that the circuit only consists of resistors and power supplies. And at chapter 2.1, we will discuss Ohm's law first. In chapter 2.1, we will discuss Ohm's law. So different materials, they allow charges to move within that material with different levels of ease. So the physical property or ability to resist current is known as resistance. And the conductor designed to have a specific resistance is called resistor. For different types of materials, it has different types of resistivity. And we can calculate the resistance using this equation. We can see it is proportional to the resistivity, and also it is proportional to the length of the inductor, and it is inverse proportional to the cross-sectional area. There are different types of resistors, and it is common in the electrical engineering lab to use these resistors. And in our lab, we will use these resistors. We will introduce how to read the resistance from the resistor in our lab course. Of course, the symbol of the resistor usually use R to represent it, and the symbol is like this. Yeah, this is that I mentioned that the resistor with a color code, and we can read the resistance from the colors, and we will introduce this in detail in our lab course in the first lab. And of course, our multimeter can measure the resistance. You can measure the resistance directly. And there are also variable resistors, which means that the resistance can be adjusted, and they are labeled, the two types of labels in our circuit. So Ohm's law. Ohm's law is the relationship between voltage and current. We can see from the VI curve, we can see that with the increase of current I, the voltage V will increase, and the slope is R, is the resistance. So to calculate the resistance, we can use V over I to calculate the resistance. In ideal case, the VI, the relationship between V and I is linear. However, in real situations, and when the current exceeds a certain threshold, the relationship is no longer linear, it is nonlinear. But in this course, we will analyze the linear relationship. So the linear relationship is that V equals R times I, and sometimes we know V and R, we want to calculate I, we use the equation that I equals V over R. And the conductance, in the previous slides, we discussed the resistance R. And we can also define the conductance. We use the symbol G. So it is the quantity widely used in circuit analysis. It is the reciprocal of the resistance. It describes the ability of an element to conduct electric current, and the unit is Siemens. Siemens. For the resistance, we use R, and the unit is ohms, right? So we can also describe the Ohm's law using the conductance. I equals G times V. And there are two extreme possible scenarios. The first is that when R equals 0. The second one is R equals infinity. There are two basic circuit concepts, that is a short circuit and open circuit. When R equals 0, we call it short circuit. And when R is infinite, we call it open circuit. So when open circuit, the resistance is infinitely large. So the current is close to zero, is zero. Yeah, is zero. And when R equals 0, according to the Ohm's law, the voltage drop between these 2 points is 0. So we already know from the previous lecture that the power can be calculated using V times I. And today we learned Ohm's law. So V equals I times R. By plugging the V into the equation, we can obtain that P equals I squared times R. And also we know I equals V over R, Ohm's law. And by plugging I into this equation, we can get that P equals V squared over R. So this is equation 1, equation 2, equation 3. We have 3 equations to calculate the power. And also we know that R equals 1 over G. So we can calculate the power using the conductance. So we get equation 4. So let's take a look at the first example. The voltage and the resistance is known, so we can use the equation that P equals V squared over R. So that is 12 squared over 2 times 6, right? So this becomes, so this is 0.072 watt. Yeah, this is straightforward. Just use the equation. The second example, the V is unknown. The P and the R is known. We know P equals V squared over R. So the P and the R is known. We can calculate V. So V squared equals P times R. So this is the resistor is 10K. So V squared equals 36. So V equals 6 watt. That is the square root of 36. And I equals V over R. That is 6 over R. So also it equals 0.6 milliampere. And the third example, here we use the conductance, not resistance, but let's take the Vs equals I times R, but we do not use R, we use G, so that is I over G, right? So the I is 0, the G is by plugging this number, so we have, I think we have 550 equals 10 watt. And we can also calculate the power. Power equals Vs squared over R equals Vs squared over times G. So by plugging the numbers, the Vs is 10, so that is 100 times G, 50 times. So this equals that's the answer for this example. So the presence of the voltage source between a pair of terminals tell us precisely what the voltage is between the two terminals, regardless of what is happening in the balance of the network. What we do not know is the current in the voltage source. So we have a voltage source connect to the circuit, right? So we know that the voltage between the terminals of the voltage source is Vs, and it has a value. But we do not know the current that goes through the voltage source. We need to do the calculation, circuit analysis to obtain the current flowing through the resistor. For the current source, likewise, the presence of a current source connected between two terminals specifies the exact value of the current through the source between the two terminals. What we do not know is the value of the voltage across the current source. So here is the current source. So the current goes through the current source is known, is a fixed value. But what we do not know is the voltage over the current source. We need to carry out circuit analysis to obtain the voltage over the current source.